gonna talk about this free boundary problem from the model of liquid crystal droplets. So I'm very honored to have this opportunity to present this work. So the joint work with Fanghua Lin. And so here is an outline of my presentation. So firstly, I'm gonna introduce this Oseen-Frank model. And thanks for Giacomo, we're already familiar with this model. And also, then I will formulate this droplet problem as a free boundary problem. And then I will give some preliminary analysis on some geometric properties for the admissible set. And for the next part, I will give the existence of the minimizers. And for the last part, I will talk about some asymptotic behavior of the droplet in some limiting region. So here we have, so we consider the nematic liquid crystals. So they are composed of these elongated molecules. So locally they have some, they tend to align in the same direction. So you have the locally alignment of these molecules can be modeled by usually there are three commonly used models: the Oseen-Frank model, the Ericsson model, and the Landau-Digen's model. So we are going to work with the Oseen-Frank model. And the other parameter which describes the local alignment of the molecules is given by this unit vector field Nx, and it's a unit vector. And suppose this omega is a region occupied by the liquid crystals, and the total free energy of Oseen-Frank model is given by this energy density, this W. So that penalizes the deformation of the vector field N. And you have several terms that penalize the splitting of the and twisting and bending term. And also you have a non-Lagrange term. So the existence and the regularity for the minimizer was established in the work of Hart, Candelier, and Lin in 1986. So this shows that the minimizer is analytic away from a singular set. And this singular set have a Hausdorff dimension is strictly less than 1, so we've got the partial regularity result. And in particular, if we take some special parameter, like K1, K2, K3 equals to 1, and K4 0, the energy function now reduced to this Dirichlet energy of the unit vector field. So this is the energy functional for, so this minimizer N becomes a minimizing harmonic map. And this is a brief review of the Oseen-Frank energy. And so we are interested in the liquid crystal drops, that when liquid crystal material are dispersed in some other medium, like the isotropic fluids, for example. And in this case, the liquid crystal will be contained in a small drop. And so the shape of the optimal shape of the drop is determined by the interface energy. So you have interface energy. And according to the theory developed by Chandrasekhar, Friedel, and Ericsson, so the surface energy can have this form. So this energy density depends on this n dot nu, which is n is the director for the alignment of the molecules, and nu is the normal vector on the boundary of the drop. So omega is a drop of the liquid crystal. And usually F can assume to have this form. So this mu and lambda are two coefficients, and the mu is positive, and lambda is can be negative or positive. So with this surface energy, we can define this variational problem for liquid crystal droplet. So we consider this omega is in the 2D or 3D domain, and this N is a unit vector field. And we have this problem that we need to find the minimizing pair, omega, the domain, and N, that minimize this energy function that have two competing parts. The first term is elastic energy, the second term is surface energy. And we have the constraint, the fixed volume constraint. The omega is, the volume of omega is a fixed constant. So this gives a free boundary problem for the most general interface energy. And in some special region for the parameter, we have some special boundary condition for the director field N on the boundary of omega. So if we look at this interface energy, if we consider lambda is positive, and mu is considered we assume is very, very large. And in this case, we want this n dot mu to be small, to close to 0 on the boundary. So in the limiting region, we will get this problem B. So we have, again, the two terms, the elastic energy plus this interface energy is just the parameter of this domain. And we have the two conditions, which first one is the fixed volume condition, and the second one is that n is orthogonal to the normal vector on the boundary. So this is called the tangential arching boundary condition. So this is one limiting region, but in another limiting region where lambda is negative, so in this case, to minimize the interface energy, we want this n dot mu is equals to 1. So in this case, n just point to the normal direction on the boundary. So now we have this problem, the problem C here. So these two problems, what I described just now is a very, actually very not rigorous way to derive these two models. But actually, these two models can be derived rigorously from the general Ericsson model. In the recent work of Lin, Wang on CPAN, they can derive this model from the sharp interface limit of the Ericsson model. So they can rigorously have this tangential arching boundary condition or this normal arching boundary condition for the droplet problem. So, so now the first analytical result on this free boundary problem ABC was given by Lin, Peng in '96. So they assume that this f is a general continuous functional, and they can establish the existence of a minimizing pair among all the convex domains. And also, among all the convex domains, they can have the existence for problem B and problem C. And in particular, they have the uniqueness for the minimizer for problem C, which is just given by a ball. So the optimal drop is a ball for the normal arching boundary condition. So, so in their analysis, the convexity assumption on the domain is necessary, because if you have a sequence of convex domains, then you can, for the convex domains, have some good compactness properties, such as you have a limit of the domain, and also the normal vector field on the boundary will also converge in some good sense. That's for these convex domains. But if we remove this convexity assumption, then the problem becomes more challenging. And so in a recent work of Li and Wang in 22, so they established the existence result in a more general domains, that they assume that they remove the convexity assumption, but they assume this omega is a so-called M uniform domain. So in this case, this M uniform domain just gives some it's almost the inner and outer corkscrew condition for this domain. So basically, they also assume that this domain has some regularity, satisfies some regularity hypothesis. So for the general problem, problem A, so it's very possible that one can one can establish some general existence and partial regularity result for the minimizer. And so that this omega, we can assume this omega is in the SPV function, and also the director field is in the SPV space. And we can have the existence and partial regularity. But such a general result will not give us, will not show the profile of the minimizer. So we don't know that if some particular shape, like the ellipse, is a minimizer or not. We don't know. So our work, we are interested in to verify some particular shape, some specific shape of the optimal shape for the liquid crystal drop. So basically, this is a particular shape that we want to verify in our work. So we are particularly interested in this so-called tectoids. So this shape is an elongated drop, and in two-dimensional space, you see its boundary have two singularities at two endpoints, and they will form two cusps, so very sharp angles. And so we will build a model that such that the minimizer will look like this shape. And actually, this shape has been observed in experiments and numerical simulations for a long time. And we will consider two-dimensional free boundary problem. And also we consider the director is satisfy the tangential arching boundary condition, which means n dot mu is 0 on the boundary. And we simply take the decay energy of n. So in the two-dimensional problem, also this n is a two-dimensional unit vector, so it's on S1. And also we assume that this droplet domain is symmetric with respect to the x-axis. So therefore, we only need to consider the upper half of this droplet. And then I will show you the assumptions of our boundary curve. So now we have a boundary curve which is given by gamma. So sorry, here it should be gamma. So gamma is parameterized by this xt, yt. And so this is our curve gamma. And we say the domain is enclosed by this gamma and the x-axis. So this is our half of the droplet. And we assume that gamma is a rectifiable Jordan curve. And we parameterize it by the arc length. So here we assume that x prime square plus y prime square equals to 1 almost everywhere. So therefore this t is from 0 to the length, to the total length of this curve. And this curve starts from one point, is minus a0, to another point on the x-axis. So this a is not fixed. A can be changed according to this gamma. And the fixed constant is the volume of this, is the area of this domain. So the area enclosed by this gamma and the x-axis is a fixed constant. And also we have an extra assumption on this curve is that we assume that x prime is positive, it's not negative everywhere. So which basically means that we want this curve to always move from the left to the right if you go along this curve. So we don't want the curve go this way. But we can allow the vertical part of the curve. So it can go perpendicular to axis, but we don't want this curve to go backwards. So this is an extra assumption because so in mind we have this particular shape of the tectoids. So in the assumption we want this curve to stay close to this shape of the tectoids. So now this is our assumption on the curve. So then we have in the director field n, we have the tangential arching boundary condition. So which can be given by this, because we have the arc length parametrized of the curve gamma. So on the boundary is given by the arc size of y prime. And on the x-axis is just 0 by the symmetry assumption. So And also, okay, so sorry, I forgot to mention that because we consider a two-dimensional unit vector, so we can lift it as a function of an angle function theta. And the Dirichlet energy of n is just given by the Dirichlet energy of theta. So in the case that n is in H1, this lift is to this angle function is valid. So then we define our admissible set for this gamma. So the gamma satisfies the previous assumption, and also this theta, this angle function now is defined on the boundary of omega gamma. So it's defined on gamma and the x-axis, and then we require that it have a finite energy extension inside in the interior. So because it's minimizing this Dirichlet energy, so the theta is just a harmonic function inside the domain. So, and also we have the last one is the fixed volume, fixed area assumption on this gamma. So now you can see it's easy to check this admissible set is non-empty. You can just have a smooth graph and you can check if the energy is finite. And then we are ready to give the final variational problem we consider. So we consider the gamma, we consider this energy functional, that the first part is the Dirichlet energy, plus the length of this curve gamma. And this theta is completely determined by this gamma in the sense that it is a harmonic function in the inside the domain, and on the boundary is defined as a tangential direction of the gamma. So this is, so you can see, basically this is just a functional that's completely depending on this gamma. So now we have the variational problem. And so now we can see that this admissible set, the definition is in a very abstract way that we don't know what should this gamma satisfy to have the finite energy extension inside. So the next thing before we have the existence of minimizers, we want to get some properties of this gamma in the admissible set. So they should satisfy. Basically, we will show that it's a chord-arc curve for this gamma. And first of all, I will give a simple observation for the minimizer. So we assume, so throughout the rest of the talk, I will assume this fixed volume is 1. So this is just a parameter. And if we have a minimizer, then the first observation is that this minimizer should be simply connected. So this minimizing curve cannot intersect with the x-axis at besides 2 endpoints cannot intersect with this x-axis at other points. So the proof is straightforward, just using the minimizing property. So you assume you have another intersection inside in the middle. So this intersection will cut this omega into 2 parts, omega 1, omega 2, and also cuts the curve in 2 parts. And then you're rescaling these 2 subdomains so that they have a volume 1, and you can compare their energy with minimizer, and you get a contradiction. So this is an easy observation, which will be useful when we prove the existence of minimizer. So now we don't assume gamma is a minimizer. We just consider gamma is in the admissible set. So satisfy the finite energy, satisfy that the theta defined by this gamma will have the finite energy extension. So the first property is called this 3-point property, such that for any 3 points, Z1, Z2, and Z3 on this gamma, it satisfies that the distance between Z1, Z2 and the distance between Z2, Z3 is bounded by some constant of the distance between Z1, Z3. So the main idea is if you have a 3-point is J1, J2, this is J2. This is J3. So the distance of this is bounded by the distance between J1 and J3. So which means they cannot form this very sharp angle.
Maybe you should raise the board.
Sorry?
No, people cannot see.
Oh, yeah, I should. Maybe. So basically, this says this property tells us that if you have 3 points, J1, J2, J3, you cannot form very sharp angle. So this, and the ratio of the distance between these 2 points can be controlled by the distance of these 2 points. So this is our first property. And the proof is quite, the idea is quite simple. You just use the energy, and I will show you, use this picture. So if you have, assume by contradiction, you have a 3-point that forms very sharp angle. And then from the point from J1 to J2, you will have because of tangential action boundary condition. So most part of this curve, which is shown in the color of yellow, you will have this theta is close to half of pi because it's going upwards. And then similarly on the curve between Z2 and Z3, you will have this theta is close to minus half of pi because it's going down the very steep way. So therefore, then you calculate the energy in the polar coordinate with the center Z2 and with if you have a circle with radius r, and it will intersect this curve at 2 intersections, and one have the angle very positive and one have the angle close to minus half of pi, and so you have a large Dirichlet energy on this circle, and then you integrate with respect to r. So in this way, you will find the Dirichlet energy is bounded below by some log of c. So here c is just the ratio of the distance of this 2 point and this 2 point. So if this c is large enough, we will contradict with finite energy. So this is a simple idea for the 3-point property. And from this 3-point property actually gives us some regularity of this domain omega. And the most important thing for this property is that we can extend this theta to not only define on this omega gamma, but to define a larger domain. And also we have the control of the norm of the theta. So this is we use some classical result in the theory of conformal mapping. So it's due to our force that if you have a Jordan curve gamma and it is a quasi-circle, if and only if it satisfies the 3-point condition. So the quasi-circle is the image of the circle that under a quasi-conformal mapping in a complex plane. So, and in particular in 2-dimensional space, a quasi-disk is equivalent to the Sobolev extension domain. So that's due to joints in 81. So the quasi-disk is just a domain enclosed by this quasi-circle. So therefore, with some slight modification of this classical result, we can get this lemma. So if we assume that gamma is in our miscible set with finite energy, we can find a constant that only depends on this energy, such that this theta can be extended to the whole plane, R2, and with H1 norm uniformly bounded. This constant only depends on this energy. So this is a consequence of this 3-point property. And further, we can prove that gamma is actually a chord-arc curve. So by chord-arc curve, it means that the length of the curve between any 2 points on this curve the total length is controlled by a constant times the distance of these 2 points. And also this constant also depends on this energy. So the proof of the chord-arc curve is actually very similar to the previous lemma of the 3-point property. That is that if you have the arc length is very large compared to the distance of these 2 points, then this curve will have to have lots of fluctuations going up and down, and these fluctuations will generate large Dirichlet energy. So the only tool we use repetitively in the proof is the co-area formula. So it's a similar idea, but the proof is more technical. So maybe I will skip this part. So the idea is similar. So then further we can show that this curve is actually a so-called vanishing chord-arc, which means at smaller and smaller neighborhood, if the distance of Z1, Z2 is very close, then this length of the curve is almost 1. So it goes to this constant of the chord-arc property is almost 1. So that means it's in a smaller and smaller neighborhood, this curve will be more and more flat. And then from the result of Koenig and Toro, such that if this gamma is more and more flat in the small scale and also is vanishing chord-arc, then that means the normal vector is in the variable space. So this is a result for this chord-arc curve. So therefore we have we know that our curve in the miscible set should have the normal vectors in variable. And then I will surprisingly actually our curve in the miscible in our problem is very close to another terminology in the theory of Teichmüller space that which is called the Weil-Petersson curve. So there are many definitions of this curve, but one definition is characterized by this map F. That if you have a conformal mapping, F maps unit disk to a quadratic disk, and then this if the log F prime and you take another derivative, it's in the L2 space, then this the boundary of this quadratic disk is called the Weil-Petersson. In the Weil-Petersson class, actually our curve by elementary analysis, you will show that our curve and this Weil-Petersson curve satisfy many similar properties locally. So our curve is not in this Weil-Petersson class because it's not a closed curve, it's not a quadratic circle, but locally they share the similar property. And actually, in this work of Bishop, he gives like 26 in total. A lot of characterizations of this Weil-Petersson class, and many of these properties can be generalized to our problem. So with slight modification of the proof. So here I just list some of these properties. So the first one is about this. Since we already parameterized our curve by arc length, so this arc length parameterization is in the Sobolev space H3 So and also we have some other properties, and actually we can list more properties for that's satisfied by our problem. And now we get some preliminary analysis on the miscible set. We can discuss the existence of the result, existence of a minimizer, and it's just by direct method of the calculus variations. So we have existence of minimizing this functional, and this gamma and the axis will form two cusps at the intersections. So I will brief explain the proof. So we have a minimizing sequence and gamma I, and also we have the corresponding omega I and theta I defined. So the theta I at first is only defined in this omega I, but because we can extend this theta I to define on a larger domain, so we can find a large ball BR that does not depending on I, such that all the theta I are uniformly defined on this domain BR, and with H1 norm is uniformly bounded. And then we take to the limit, we find a subsequence. So for the first three convergence property are just straightforward. So we have the omega I will converge to omega, strongly in L1, and for the limiting domain, some set of finite perimeter. And the theta I will converge in theta, weakly in H1, and strongly in L2. And also this gamma I will converge to some chord-arc curve gamma. And the only thing we need to verify is that for the limit domain, because we take the convergence of the theta and omega separately, so we need to verify that this tangential action boundary condition is preserved for our limiting domain on the boundary of the limiting domain. So the proof is we use this Green formula. So first of all, we consider this quantity, that is the integral of, for any phi is a smooth test function, and we have this quantity phi ni take divergence, integrate on omega I, will converge to this limit integral. This is due to the convergence of ni and convergence of omega I. And then we use the Gauss-Green formula to write this integral on the boundary. So you have a, and then you have that as I go to infinity, this integral will converge to this integral. And this integral is zero because it's ni dot nu I is zero. So therefore, you have a tangential action boundary condition for the limiting domain. Because this test function phi is arbitrary. And also for the behavior near the intersections, we can prove that, so for example, near the one of the intersection, so in this, with a ball of radius r, we can show that this height and this distance to this boundary, this ratio will go to 0. So that's basically what this lemma says. And this gives that in the smaller and smaller neighborhood of this point, you will have a very thin domain in the limit. So now we have the existence for the minimizer and also for the asymptotic behavior at the intersections. Then for the regularity problem, actually we know very few about the regularity. So for example, the first question is whether or not this gamma is a Zhiyuan curve. So it's hard to prove. And further, ideally one can conjecture that the minimizing gamma is graph of some nice function, and this slope can be uniformly bounded, so that it can avoid this vertical part. It will behave very nicely in this way. But for this problem is difficult because for the local irregularity of the free boundary, this tangential action boundary condition is very rigid. So if we consider the general fx, instead of we require to be tangential everywhere, if we consider more general interface energy, then we can have the partial regularity for the boundary. But for this very rigid condition, will make it very difficult to get the regularity. And to see this, we will actually derive an Euler-Lagrange equation for, we assume that this gamma is given by this graph of a Zhiyuan function f. And then we derive the equation as satisfied by this f. So this is the Euler-Lagrange equation. And the lambda is a Lagrange multiplier, and the first term comes from the length of this graph. So it's a familiar term. Well, the remaining terms comes from the Dirichlet energy. And here you can see we have some very non-local operator here, which is a Dirichlet to Neumann operator, because we only have the value of theta on the graph, but here we have the normal derivative of theta on the graph, and so we believe that if we can analyze this equation, will give us the regularity of this graph f, but we didn't succeed in get the regularity property for this equation. So it's still open. And okay, have 5 minutes.
8 minutes.
8 minutes. Okay, so I will briefly discuss about the asymptotic analysis in some limiting region. So we want to study the behavior of the minimizer draw. Minimizing draw as the volume goes to infinity or go to 0. So one must consider this problem from the scaling point of view that you have 2 parts of energy. So this is your problem, original problem. And this first Dirichlet energy is of dimension 0. And this energy is of dimension 1. So therefore, if you have the volume of this domain is very large, then this term will be the dominating term in the energy. Otherwise, if this volume is very small, then this term will be the dominating term. So therefore, we construct an equivalent problem of this problem. So now we let this v to be a parameter in the equation, in the energy functional, and we fix 2 endpoints of this curve gamma. So before the intersection of gamma and the x-axis are not fixed, now we fix them to be -1, 0 to 1, 0, and then we have these 2 parts of the energy. So the minimizing profile for the drop is similar to this problem after scaling. So now we have this coefficient as 1 over square root of v. So as v goes to infinity, we can say this term will go to 0. So basically, the minimizer will only minimizing this term. And it is well known that for the minimizer of this functional is just given by the half circle. So this is the large volume limit that this gamma, the minimizing gamma as v goes to infinity, will converge in to this half circle gamma star. And then in the small volume limit, we have that when v is very small, then this term will be very large compared to this term. And then we have the Dirichlet energy will be almost the order of v. So here is that if this domain have the volume v, so in this case we want this to be a very elongated drop, such that this elastic energy is small, so it's all these director fields are almost parallel to each other. And if the volume of this is v, and then we can have that the Dirichlet energy is almost the same order of the volume. And in this case, going back to this problem d prime, we have that the height of this curve gamma will be almost will be of the order v to the power 1/3. And then we can write, if we write this as a graph of f, So f is some like Zhiyuan function, and we stretch this graph of f to the graph of g. So we just by dividing v to the power 1/3, then we can get this graph of g is actually a normal shaped droplet. And then we can use gamma convergence technique to get the asymptotic equation satisfied by this g as v goes to 0. And also we can get the asymptotic profile for this limiting minimizer g. So that's what we've done for this limiting region. Thank you for attending.
Thank you very much.